Right. So when we are talking about nuclear decay, we are talking about a reaction that's going to involve the atom's nucleus. Okay, this is where when they talk about nuclear, why is it not letting me write? When they talk about nuclear, are you gonna let me write now? Nope, you're not. Okay, it's just gonna be incorrigible. Ladies, do we need to switch seats? Okay. So when we talk about nuclear chemistry, where they get the word nuclear is from the atom's nucleus, because that's what's changing. And remember the two parts that are in the nucleus. What are the two things that are in the nucleus? Protons and neutrons. So we're having changes in the numbers of these, and that is what is altering when we're talking about radioactive chemistry. So radioactive elements are going to emit radiation because their nuclei are unstable. And we saw, gentlemen, do we need to move? We saw about that instability last week when you were doing those atom models on that FET. Do you remember if you added too many protons or neutrons and compared to the electrons, remember the thing got unstable and it started shaking? Do you remember doing that in your simulation? Okay. Normally, if you're thinking about the nucleus, remember they've got protons that have positive charges and neutrons that have no charge. If you have a bunch of positive charges together, what would you expect to happen? What happens with like charges? In terms of electromagnetic forces, what happens with like charges? Positives do what to each other? Repel. They're going to push apart. So the nucleus, if we're just looking at electromagnetic forces, you would expect that nucleus to push apart and not stay together, but it does. So there has to be an overriding force that overrides that compulsion, okay, to push apart. And that is called a strong nuclear force. And that's what's going to hold these positive ions or positive charges together. But this strong force only works over very small distances. So if you keep adding protons and neutrons and more and more and more, you get too many of these. This strong force can't hold everything together. And that's where you start getting radioactive decay. It decays or falls apart into other items. Okay. There are several types of nuclear radiation. We are only going to look at 3 of them in this course. So the 3 that we look at are called alpha, beta, and gamma. So alpha is essentially a helium nucleus. So a helium nucleus would be 2 protons. That's what makes it helium. And then it would have 2 neutrons. Beta is essentially an electron. And gamma is just pure energy with higher frequency and more energy than an X-ray. So you know X-rays are dangerous if you have too many of them, right? A few during the year aren't bad. Gamma is the same way. You can have some exposure to this, but too much can cause a lot of problems. Okay. When we talk about alpha radiation, again, that's 2 protons and 2 neutrons. It's going to have a +2 charge, and we abbreviate it like this. When I draw that myself, it looks kind of like a fish without the tail connecting it. Okay. This will do a lot of damage if it can get into your body, but just a sheet of paper will stop it. So clothing would stop it. So it's less likely that you're going to get this in your body unless you have like some major kind of exposure. Okay, so we're going to talk about how we do our equations for this. I'm going to rewrite this down here so it's a little bit bigger, but you can just keep it where you're at. Now, we've talked about these symbols and what they mean. This top here is what? Neutrons and protons, and our bottom is protons. Okay? We are going to take this and we're going to emit an alpha particle. Okay? So remember, the alpha particle is 2 protons and 2 neutrons. So that is 4. We've got 2 protons, and that's essentially a helium nucleus. And now we've got to figure out what we're going to be left with. So if you think about this as 2 separate problems, 2 separate math problems. Okay. For example, if you had in elementary school a problem that looked like this, what would you fill in the blank there with? 222, because 222 plus 4 would give you 226. Okay, now we're going to do the bottom part here. 88 equals 2 plus blank. What would I put in here? 86. And then I'm going to go over to my periodic table and I'm going to find element 86. So element 86 on my periodic table is Rn. Serenity's over there if you want to sit next to her. Okay, does that make sense how we do that? You think of it essentially as 2 separate math problems. So the top line goes together and the bottom line is going to go together. Does that make sense? Is it easy enough? And then where do we get this? We look at this value on the periodic table and that gives us this symbol. Good? All right, beta radiation. So beta radiation is made up of a beta particle. That is essentially an electron. What happens is your neutron, in a simplistic explanation, your neutron is a proton and an electron put together. Okay? That is why it's neutral, because you got a positive and a negative coming together, so it balances out that charge. If we think back to, let me see, did I have that chart up here? I don't think I did. I showed you a chart in your notes the other day that looked like this. Okay. Remember, with that chart, do you see how the neutron has a slightly higher mass than the proton? That's because this neutron is essentially this and this put together. And that's why it gives you a slightly larger amount here. And that's why its charge is 0, because -1 plus 1 is 0. Okay? So it has a charge of a -1, and we abbreviate it like this. If I draw that out, it looks like a capital B that's leaning just a little bit, and it has a tail down here. This is called a beta particle. And you can stop that with a sheet of aluminum foil. So something as small as a piece of aluminum foil will stop the beta particle. Okay. All right. Let's look and see what's happening in terms of our atom here. Okay. We have carbon 14. Carbon 14 has 6 protons. So I've got those in the blue here. And we have 8 neutrons. Okay, because 14 minus 6 is 8. So we've got our neutrons here. We've got our protons. We have where we're going to take one of those neutrons, and what happens to it? What do we say happens to one of the neutrons? What is a neutron essentially? It is a proton and electron. Okay, so what's going to happen is that neutron is going to split. Okay, so that neutron is going to split. It's going to go away, and it's going to produce an electron. That electron is going to leave the atom, and it's going to create then that electron that leaves. That's your beta particle, and it's going to leave behind a proton. Okay, so this is what that's going to look like in the end. So at this point, I now have how many protons? 7. Okay, what is my mass? 14. What element is this? What element is number 7? Nitrogen. They looked this value up on the periodic table and found that it was nitrogen. And then we also have this guy given off. Okay, and he's going to fly out of the atom, and he can do some damage. So this guy right here is an electron. The electrons, we said, have no mass, and he's an electron. Okay, now we need to balance out this material here. So if we have 6 equals 7 plus what? What would I put here to get 6? -1. Okay, so this is the symbol that you use for a beta particle, which is essentially an electron. Does that make sense? All right. Our last guy then is going to be gamma radiation. Gamma radiation is pure energy. It has no charge, and it's abbreviated. It looks kind of like a funky Y. Okay, when I draw that, I usually draw it like that. Maybe that's a little dramatic. So something like that. Okay, kind of like a fish on its nose. We can use several inches of lead to stop this. This is the really damaging stuff because it's hard to protect yourself from this. As opposed to like X-rays where they put that lead apron on you, okay? This would be several inches of lead. I mean, that's a super thin layer of lead. Can you imagine? And you know how heavy that apron is when you get dental X-rays? You know what I'm talking about? Okay. That is a relatively thin layer of lead. Can you imagine several inches on your body? It would like crush you. Okay. So that's what it would take to stop this. So it's really hard to stop this radiation. All right. When we go to do our equations for this, our symbol for gamma radiation is 0, 0 because it has no mass, it has no protons. And now we're going to write the symbol over here. Well, this again, we're just going to split this off as 2 equations. What would go on the top what would be here? What plus 0 gives me 238? And then my bottom equation, what goes here? What?
92.
Yes. So 92 plus 0 gives me 92, and that element is uranium. So you're just giving off pure energy here in this equation. Okay? So you have